At a busy railway junction, a mechanical switch determines which incoming track a heavy train follows to reach the main line. In digital logic, this routing is handled by a multiplexer. Within a processor, data frequently needs to be routed from different sources to a single destination. For example, when saving data to a register, the system must choose between a result from the arithmetic logic unit or a value retrieved from memory. A multiplexer manages this selection. This 2-to-1 multiplexer routes in 0 or in 1 to Y, controlled by cell. Underneath are logic gates. When cell is high, the bottom AND gate passes in 1. When low, the NOT gate enables the top AND gate to pass in 0. Understanding how these signals are physically routed at the gate level provides the foundation we need to translate this logic into our first Verilog module. The most direct way to code this is structural modeling. Often called a netlist, it's a line-by-line description of each physical gate. We declare internal wires C, D, and E as physical traces linking our gates. Next, we instantiate the logic primitives. The first signal in parentheses is always the output. Here, C is the output, driven by inputs A and S. Structural modeling provides precise control over the hardware implementation. However, manually defining every gate becomes difficult to manage as the number of inputs increases. A more efficient method is data flow modeling. Instead of defining every single individual gate, we use continuous assign statements to describe the Boolean behavior of the circuit. This ternary operator replaces the gate list. It evaluates cell to output in 1 or in 0. Pause here to consider a 4-to-1 multiplexer. Using a 2-bit selector, we check the most significant bit first. A nested ternary oscillation then chooses the final input. While nested operators are cleaner than manual gate lists, the code can still become difficult to read as the input size grows to 16 or 32 bits. Declaring dozens of discrete inputs like in0 through in31 is inefficient and prone to errors. Vectors solve this by bundling discrete inputs into a single bus, declared here as a 4-bit input array. The assignment becomes a single, scalable line. We use the selection signal as an index to directly pick the corresponding bit from the input bus. Using vectors in data flow modeling allows the code to remain readable regardless of whether you are switching 4 signals or 400. These multiplexers are building blocks for complex components. In an ALU, multiple multiplexers route data through arithmetic paths based on the executed instruction. By acting as traffic cops, these blocks allow a single data path to handle multiple operations without signal interference. When you require control over the specific physical gates or need to verify a design at the transistor level, structural modeling is the standard choice. For most RTL designs, using data flow modeling with vectors provides a cleaner, more readable description of system behavior. Alternating between abstract data flow and physical gate structures lets you adapt code to specific hardware constraints. You can download a summary cheat sheet in the description below.